Welcome everyone. In this video, we will take a look at some limits at infinity. I've set out three cases that you might see, and we'll take a look at an approach to each. So let's take a look at part A. We have a limit as x goes to infinity of another rational function. We have negative x cubed plus 2x squared minus 3, and then divide by x minus 4. So there's a couple things to keep in mind when we're thinking about limits to either positive or negative infinity. And I'll try to note those on the top here. One is the sign of our limit, and the other is the direction. So where are we headed, and really with the sign, and what kind of side are we going? So in terms of sign here, let's just consider, again, the leading terms are going to be what rules these rational functions. So we have a negative x cubed as the leading term on the top and an x term in the denominator. So we can consider as x goes to infinity or gets really, really large, the numerator here is going to overpower that denominator, meaning that in terms of our direction, we are tending off towards an infinity of one kind or another. The kind of infinity is based on the sign. We want to be careful of what sign we're going to put to this. So we know that this is going to tend off to infinity, again, because of the ratio of leading terms. But we want to consider here what type of infinity. Is it going to be a positive or a negative? And so if I consider putting a large value or larger and larger values into x here, that numerator we know is always going to be negative, and that denominator is always going to be a positive. So if I take a ratio of a very large number that's negative divided by a positive, this would give us a negative value in response. So we can say that this limit here is going to tend off to negative infinity, both giving us the direction and the sign of that limit value. Part B, we'll take a look at. Also, we want to, whenever we have limits at infinity or negative infinity, again, we want to consider the leading terms. So the leading term in this part B is going to be x squared and x cubed. So in this case, the roles here are reversed. The cubed power will start to overpower, in other words, get larger and larger quicker than the x squared power. So if I have a denominator that's growing faster than its numerator, I know that that fraction is going to be tending down towards 0. And in this case, since it's tending down towards 0, we would just consider that as 0. There's no sign to consider there. It's all going towards 0, regardless if it's a negative infinity or a positive infinity in that type of a ratio, where our denominator outranks or outpowers the numerator. So that would be a 0 for our limit. And then final, take a look at the cases where we have even powers or even degrees on our leading coefficients. So this is a limit as x goes to infinity. We have a 3x squared in the numerator and a 2x squared in the denominator. So both of these two terms, in terms of their variables, are growing at the same rate. But we'll notice that one has a coefficient of 3, one has a coefficient of 2. So in this case, we are going to be growing, and this will have, in other words, an horizontal asymptote at this ratio 3 to 2. Because the numerator and denominator will be growing at the same rate other than that coefficient of 3 and 2. So just to kind of give a little bit more rigor to that result, let me give you guys a little bit of a more algebraic explanation to 2 over 3. If we consider this limit and rearrange some terms a little bit, let's consider dividing all of the terms in our function here by the x squared, that leading power. So if I divide by x squared everywhere, we can consider the first term, 3x squared, will be a 3. We'll have a plus 2 over x divided by, this will become a 2, and then dividing the 9 will be a 9 over x squared. Now let's just consider the limit as we have it to infinity. If I consider this limit as x goes to infinity, the constants will stay the same. So if nothing happens to a 3, the 2 to the 2 over x term here will tend off to 0 as x goes to infinity. 2 will stay the same, and the 9 over x squared will also tend off to 0. So this gives us the result that this limit value will be the 3 plus 0 divided by 2 minus 0. So this also gives the result of 3 over 2, which we got in kind of our first analysis. So either way you go about it, this will give you a limit value of 3 to 2, or 3 halves. So in summary here, there's our kind of 3 cases in terms of limits at infinity, where the numerator power is greater than the denominator. That's part A. In part B, we had a degree higher in the numerator than the degree is higher in the denominator than the numerator. And then in part C is where we have the degree of the numerator and denominator are equal, and we need to consider their coefficient ratio. So I hope this is helpful when taking a look at limits at infinity for at least rational functions. In our next videos, we'll take a look at more limits and introduce some derivative topics.